Hi guys, it's teardown time again. Today, rather interesting device, but simple device. And I will show you in a minute, in a jiffy, what it is. People that understand German already know what it is because it's written all over it. Anyway, a couple of years ago, I wanted to design an discharge device for large electrolytic capacitors or large capacitors, high voltage capacitors, to discharge them safely. Till that time, I had a resistor that I always misplaced somewhere and always was looking at it to find it. And at the end, mostly I took the screwdriver and shorted the capacitor leads. As you know now, probably I have to do with switch mode power supplies and high power electronics. This was not a solution to continue because the power of the devices I was building and designing was getting bigger and bigger. Shorting this kind of capacitor, the small one, I don't have anything to show you how big it is. Anyway, it's okay. It's not okay, but it's doable, yeah. It will make a big bang, and that's it. But starting with these ones, then it's not only just a problem, it gets dangerous, yeah. These ones, I remember I never discharged them with a screwdriver. I used some kind of a resistor for that. And even worse, this kind of stuff, these ones, 1000 microfarad, 350 volts. Yeah, this is dangerous. This is not only not good for the capacitor, for the screwdriver, it's dangerous, yeah, because they have so much energy inside them, yeah, that I had quite a few times glowing projectiles from the screwdriver flying around. So that's a no-no. So this is why I wanted to design a safe discharge device that would show me if the discharge is still running, in a very crude way, what is still the voltage in the capacitor? Is it just above a dedicated value, etc.? Nothing really fancy, but with a little bit of information. So I thought before I design this thing and make PCBs again, etc., let's take a look on eBay. If there is something perhaps somebody else built, I can use it, I can modify it, or even more, if there is something professional. And what do you know? I find this. I found surplus, industrial surplus, I think it's called a surplus shop, yeah, that had quite a lot of those. And these are professionally made for a company, from the company. It's made by SOLUTRONIC AG. I'm sure that they were intended to be a commercial device. They were just built for the internal usage, because SOLUTRONIC is a company, a large company in Germany that makes MPPT, solar inverters in general, and everything that has to do with photovoltaic, and that means power. So they built this. In German it says discharge resistor up to 1000 volts, blah blah. Keep it at least 15 seconds and be careful, and I mean, many things. And the interesting thing, these two indicators. They have one indicator that says that the voltage is still over 30 volts, and the red indicator is for discharge in progress running. How do you make that without an external power supply? It is just two leads. That means that between 1000 volts down to 30 volts, there must be some kind of constant current design inside that lights this LED. And this cannot be just a resistor. Same thing this one. You have a 970 volts span that these two LEDs have to operate. This one all the time and just stop when it goes 30 or less. And this one, yeah, I know that it shows as long as it is running. It dims down, but it keeps showing that the discharge process is running. Yeah, and the discharge process starts by pressing this button. So, what do you think, how they did it? And the reason why I'm showing you this device is not because I want to show you the resistor, because inside this there are some very interesting tricks they did for these two LEDs. So let's take a look what is inside. So I opened one already because I have two of those, and you see it's from SOLUTRONIC AG. It's called dis1_2, and this is how it looks. Okay, this is easy. These are the discharge resistors. But what's the rest of the stuff? For what they use this big boy here? You can see it. I don't know if you can see it. Yep, now. That's a very beefy IGBT. And I'll show you the data sheet in a minute. That's a TO247 IGBT on a heatsink. For what do they use it? Interesting. The next thing is here. It's a big TVS, a 5.8 volt TVS, but 1500 watt capable. Look at that. Then two Zeners, resistors, and the bridge. So, of course, I made the reverse engineering of that because I wanted to know what they did. And I will show it to you now, what's inside and how this thing works, and show you the interesting tricks they used. So, and this is the design. Let's have a look. On the left side, that's the button. The diodes are easy because they form a bridge. Why the bridge? So they do not have to care which lead goes at what polarity of the capacitor. It's to be careful, plus or minus. So you just put it on either way, and this works. Nice. But what's that? You remember this big IGBT I showed you? Well, sorry. Well, this is it. They are using the IGBT as a constant current source for the LED that shows that the voltage across the capacitor is still larger than 30 volt. Wow, huh? And this is how you calculate it. The current is equal of the VGE voltage, that is here 15 volts, that's a zener of 15 volts, divided by R13. It's a 4K7. If you make the calculation, you will have 3.2 milliamps here. These 3.2 milliamps have to be dissipated from this IGBT, and it is almost 3 watts at 1000 volts. And you will say, okay, but why is it not still running or lighting up when it is less than 30 volt? This is the reason why. There's another zener here that conducts only if over 33 volts. Below 33 volts, it stops contacting, and then this goes dark. A very nice design. First time when I saw it, I said, oh my God, what are they doing? They are using cannons to kill birds. But what other solution do they have? They do not have an auxiliary voltage source to do it. If they had an auxiliary voltage source, it would be easy. You can use comparators, yeah, and the voltage divider with a reference. But there is nothing. They have to use whatever the capacitor is loaded up to 1000 volts and signalize the LED over 30 volt, lit or not lit, when it's equal to 30 or less. To be honest, I couldn't think of another solution like that, because there is, again, no battery and no external, no auxiliary voltage to accomplish this. This is a nice thing, and to be honest, yeah, who cares? Why they took this big beefy 1200 volt 30 amps IGBT? Probably because they have myriads of them, because they're using it in their inverters. So they took what they had, costs almost nothing, and a small heatsink, and that's it. To be honest, I'm doing the same when I make a new design, and there is no necessity for a special chip or a special kind of transistor, IGBT, MOSFET, etc., that I have to use it. I'm just checking what I have in my stock, and I have a large stock, and from where I have the most ones, I'm using it, if it fits for my design. That's it, and most of the designers do that. But anyway, this is the first trick that is very interesting for me. The second trick is, how do they make the LED, the discharge in progress or run LED, keep lighting till the capacitor is discharged? Again, from 1000 volts down to 30. And here's the next trick. This is how they use the TVS. At the end, the TVS is not the same. Please do not misunderstand me. But from the thoughts here, this is just a high power zener. It is a 5.8 volt TVS, 1500 watt. If the voltage is something above 5.8 volt, this thing makes the voltage, keep the voltage around the TVS is then 5.8 volts, or not 5.8, it's more, that's something like 7 volts. And this is exactly what they use in parallel to this TVS. they have the LED with a resistor. And you can see the resistor is calculated for something between 5 and 7 volts. And this is how they do the indication of the discharge in progress. The rest is easy. These are the two contacts, plus and minus. One goes to the ground, and one contact of the switch goes to the ground too. The other one goes through the TVS, this beefy TVS, to the string of resistors. And if the contact is pressed, if the button is pressed, to ground. And this is how it discharges. The resistors are from the markings are probably Vitro Ohm KP298 series 6 watt, and all of them are 100 ohms. The only thing that I do not understand is this diode. Why do they use this diode? For what is it good? I do not really understand that. There is no possibility to do something reverse, etc. Anyway, if somebody knows why this diode here is used, please let me know in the comments. And now we will have a look how this thing works. Oh yes, by the way, this is the datasheet of the IGBT. You see how beefy this thing is. 1200 volts, 30 amps. Yeah. Just for information, what this thing is capable of. 390 watts at 25 degrees centigrade. This is a nice one, but again, they had it probably for their inverters or their MPPTs, and they used it. Fully understandable for me. So let's take a look how it works. To show you how it works, I'm using this rectifier and capacitor sub-assembly. This can carry 2 of these 1000 microfarads CAN capacitors. I desoldered the onboard discharge resistor to show how you discharge it. This thing already has 2 NTCs for inverse current protection when the capacitors are getting charged, and a VDR. Then here we have a beefy bridge, and all this will be connected to my isolation transformer and variac, that it is current protected, current limited. It's a current limited isolation transformer and variac that I built, that I have in a different video on my channel, the complete build. So now the mains is active, is on. You see I have the left side is the isolation transformer, the right side is the variac. Variac is not active yet. But before I activate the variac, I will make the connections. Okay, I just connected the meter to the capacitor, and you can see here that we have still 3.4 volts residual voltage on it. And now I will start the variac. I have a current limit. It is a 60 watt bulb. I have it at 3, let's go a little less, 230 volts. this is the DC voltage that this thing is charged. And now you see the blue light that shows that the the voltage across the capacitor is over 30 volt is running. And now I will discharge it. But first of all, I will close the variac and remove it. And now you see it's already going down by itself, but it says running. Zack, and over under 30 volt it goes away. We have still, the LED is somehow lit, as you can see, and we are at 4 volts. Just for fun, we will do it again. That was the inverse current to the capacitor. We have again 312 volts. LED is lighting, it indicates it's over 30 volts. Turn it off again just for sure, remove it, and do the same again. I'm pressing the button. You see how fast it goes, and it's done. And I'm keeping it up to under 10 volts. That's it. So this is how it looks. And even that the capacitor is discharged, it still has 7 volts. And if I press the button, it still discharges it. So that is what I wanted to show you for today. This thing I'm using for everywhere that I need a mains rectified voltage with quite beefy capacitors. This is planned for another project, for another design, and the design will be a variable AC power supply that would go from probably 0, perhaps not completely 0, up to 220 or 380 volts, would be current limited, adjustable, and with a frequency between 0 and 400 Hertz pure sine. But that's just a teaser for one of my future videos. So this is how it looks. If anybody is interested in the schematic, just let me know in the comments on request. You can have it. Okay guys, that's for today. Cheers.